Hello everyone and welcome back to the channel. This is Sahil Sawant and you are watching my advanced algorithm playlist, your one-stop solution for mastering design analysis of algorithms for placements and competitive coding as well. In today's lecture, that is super important. In this lecture, we are going to learn how to solve recurrence relation using substitution method. बहुत लोग रिकर्जन समझ लेते हैं बट रिकरेंस रिलेशंस जो है उनको मतलब सॉल्व नहीं कर पाते. But don't worry, we will make it extremely simple for you. In this video, we will be covering what recurrence relations are, types of recurrence relations, substitution relations, the substitution method, that is forward and backward substitution, and step-by-step solution for a particular example that we are going to look at, and finally limitations of substitution method. So without further ado, let us dive right into the topic. First of all, a recurrence relation is simply a mathematical equation that expresses Tn complexity in terms of one or more smaller values like T of n minus 1, T of n minus 2, and this appears in almost every recursive algorithm. For example, if we take T of n equals T of n minus 1 plus n, whenever a function calls itself, its running time can be represented using such a relation. Think of it like this. If you know today's work depends on yesterday's work, then that connection is like a recurrence. Let's quickly look at the most common types of recurrence relations. So type 1 is going to be linear recurrence. Every term depends linearly on the previous term. Example of this can be understood as T of n equals T of n minus 1 plus T of n minus 2 plus T of n minus 3. Second common type is divide and concurrence recurrence. This is classic DSA algorithm. That means T of n equals, let's say, 3 times of T of n by 2 plus 9n. This can be written in the form of 8T of n by b plus f of n. Okay, then moving on, there are first order recurrences which depend only on immediately previous term. So example of this can be understood as T of n equals 2 times of T of n minus 1. Then the last but not the least are higher order recurrences which depend on multiple previous terms like T of n equals 2 times of T of n minus 1 square plus k times of T n minus 2 plus T of n minus 3. Now the big question is, how do we actually solve this to find out the time complexity? Substitution method is one of the most intuitive way of solving recurrence relations. It comes in two types of algorithms, that is forward substitution and the backward substitution. इन दोनों में हम repeatedly substitute करते जाते हैं until we get a clearer pattern. Let's solve a recurrence relation. So we have an example here, that is T of n equals T of n minus 1 plus n, where n is always going to be greater than 1 and T of 1 is going to be 1 only. This is one of the most common examples that we are going to solve. So when we start expanding, T of 1 is given as 1. So T of 2 is going to be T of 1 plus 2, that is going to be equal to 3. T of 3 is going to be T of 2 plus 3, that is going to be 1 plus 2 plus 3, that is 6. T of 4 is going to be T of 3 plus 4, that is 6 plus 4, that is 10. Now observing this pattern, we can look like we are adding the sum of numbers from 1 to n. So we can guess that T of n equals 1 plus 2 plus 3 up till n. And the general form of this type of relation is given as n times of n plus 1 the whole divided by 2. Now the time complexity for this problem is going to be O of n square. Why? Because it is n into n plus 1 the whole upon 2, and n square is the biggest possible term on which we can rely for the complexity part. Now proving by induction, let's verify it quickly. So base case is T of 1 equals 1, that is going to be equal to n, that is 1 into n plus 1, that is 2, the whole divided by 2. So 1 into 2 divided by 2, the answer is always going to be 1 itself. Now by inductive step, assume t of n minus 1 is n minus 1 times of n, the whole upon 2. T of n is going to be t of n minus 1 plus n, that is n into n minus 1, the whole upon 2, plus the remaining part of n, which is giving us n into n plus 1, the whole divided by 2. Now t of n, as we had suggested, was n times of n plus 1, the whole divided by 2, and we are getting as the correct answer as well by induction. So this proves our point by substitution method. Now, do we have the same problem but from the opposite side? So first of all, we have to write the problem of using the previous terms. That is t of n equals t of n minus 1 plus n. T of n minus 1 is going to be t of n minus 2 plus n minus 1. T of n minus 2 is going to be t of n minus 3 plus n minus 2. When we put value of n minus 1 in the value of n, t of n, it is going to give us t of n equals t of n minus 2 plus n minus 1, the whole plus the remaining part of n. Putting t of n minus 2 in t of n, it is going to give us t of n equals t of n minus 3 plus n minus 2 plus n minus 1 plus n. So eventually when we try to continue it up till 1, it is going to give us t of n equals t of 1 plus 2 plus 3 plus 4 up till the value of n. Putting t of n equals to 1, we can get that t of n equals 1 plus 2 plus 3 up till the value of n, which gives us the generalized form, that is n into n plus 1 divided by 2. Same result that we got from the previous one, the time complexity is always going to be O of n square only. Even though this method is very useful, it has some limitations as well. So the first limitation is we need to guess the pattern to understand the substitution relation. Guessing may be difficult for complex relations. No guarantee that the substitution will simplify the expression, and it is not ideal for divide and concurrence recurrences. To solve this, we need to use master theorems only. So substitution works for simpler linear recurrences but not always for complex ones. And that's it for today's lecture, guys. I hope the substitution method crystal clear ho gaya hoga. If you enjoy this advanced algorithm playlist, make sure to like the video, subscribe to my channel and share it with your batchmates as well. मिलते हैं next video में where we solve recurrence relations using recursion tree method. Till then, keep learning and keep growing. Adios.